Okay, so we're going to work on examples 4 and 5. So this is example 4. I accidentally cut off where it says example 4, but we're on the second page. So we're going to go through. These are slightly different from what we did yesterday, but same setup. Okay, in a candy shop, chocolate, which sells for $4 a pound, is mixed with nuts, which are sold for $2.50 a pound, are mixed to form a chocolate nut candy, which sells for $3.50 a pound. So they've got chocolate, they've got nuts, they want to sell chocolate with nuts in it, they're going to mix it together. How much of each are used to make 30 pounds of the mixture? So we're going to set this up similar to what we did with the milk problem yesterday. So we're going to make a table. You need 4 lines going this way and 4 lines going the other way. So I'm going to have a line for chocolate, one for nuts, and then the final total mixture. And then across the top, we're going to have a column for amount, part, and total. So this looks like example 3 from yesterday a little bit, except it's chocolate and nuts instead of different percentages of milk. So we have chocolate, which sells for $4 a pound. So I'm going to underline that up here just so I don't forget what's happening. And then we have nuts, which sell for $2.50 a pound. And they're mixed to form a chocolate nut candy, which sell for $3.50 a pound. And they're asking us how much of each are used to make 30 pounds of the mixture. So we kind of need to know that 30 pounds. So I don't know the amount of chocolate or of nuts. So we're going to use 2 different variables. Do you want to use X and Y, or do you want to get more creative?
X and Y.
X and Y. Okay, JC wins. X and Y. So I have X amount of chocolate and Y amount of nuts. I don't know how much of each of those, but I do know that we're trying to make a total of 30 pounds. So the final amount is 30. Okay? And then instead of percentages, we have dollars here. So for each pound of chocolate, it is $4. So we're going to put 4 under the part column for chocolate. And the nuts are $2.50, so I'm going to put $2.50 or just 2.5 there. You can do $2.50 or 2.5, either way. And then when we get done, we want to sell it for $3.50. So what we're doing is we're taking prices that we know make a profit for chocolate and make a profit for nuts. And without doing anything too terribly crazy, we're going to try to make sure when we mix them and sell the fudge or whatever it is all together, that we're still going to make a profit. And this is about what we know people will pay based on past experience, so that's sort of our target price. So if you remember from yesterday, what we do with each of these lines is we multiply across. So X times 4 is 4X, Y times 250 is 250Y. I'm just going to call it 2.5Y to make it shorter. And then we have to take 30 times 350, which is 105. And because we have an X and a Y to solve for, we're solving for 2 things. We're going to get a system of equations. This first column is where we're going to get equation number 1. And then this total column over here is where we're going to get equation number 2. So the final is what's going to be on the other side of the equal sign. So we're going to add a certain amount of chocolate, which we call X, to a certain amount of nuts. If I mix the chocolate and the nuts together, I know I'm going to get 30 pounds total. And so if you look at this, it's just X plus Y equals 30. The final is always going to be where your equals goes. And then if we take the total, it's $4 per pound of chocolate plus $2.50 per pound of nuts. And then we're going to if we sell 30 pounds of the stuff at $3.50 per pound, we have $105. That kind of explains everything we did in the table. And now we just have a system of equations we can solve like we've been doing. And most of these work best using elimination. So what do you think we should do with these to try to solve? What would be the
top by negative 2.5.
You want to do negative 2.5?
Yeah.
She's a rebel. Anybody want to do 4 instead?
4.
Okay, let's vote. Who wants to do 4? Colton and me. Who wants to do 2.5? Okay, they want to be crazy. We're going to take the top times negative 2.5 and eliminate the y's. At least they're paying attention. Okay, so if I take the top times negative 2.5, I get negative 2.5x minus 2.5y equals, and since this isn't the way I did it, I don't know what that equals. 2.5 times, what is it?
75. I mean, because.
Negative 75? Yeah. Okay. I should have known that.
Right?
Right.
60.
Okay, and then this other one is 4x plus 2.5y equals 105. So we canceled out the y's. You could totally do 4 and do the x's if you wanted to. Then we add negative 2.5 and 4 would be 1.5x
Equals 30.
equals 30 over here when I add those together. And so if we divide by 1.5, we get 20, right?
I don't know. I didn't do it. I waited for
Yeah, I thought you guys were working ahead. Okay, so we get x equals 20. So if we go back to our original problem that we set up over here, x was the amount of chocolate, and we were measuring that in pounds. So we can go ahead and write as part of our solution, we've got 20 pounds chocolate. And then we know that we're making 30 pounds total. So if you go back to what we usually do with systems of equations, you could just put the 20 back in here for x. 20 plus y equals 30. Or you can use a little bit of common sense, like, okay, I'm going to make 30. If 20 pounds of it is chocolate, then what plus 20 makes 30?
10.
You could figure that out pretty quickly. I'll show the work just for the sake of argument, but we end up with 10, and that would be the 10 pounds of nuts because y was the amount of nuts. And so we're going to label those answers just so that we know what each piece is. Alrighty, so, and it makes sense that there's more chocolate than there is nuts, because I don't know that it would stick together if you had more nuts than chocolate. That would be an interesting thing to find out. I don't know. Okay, so the last problem, so this one is a lot like example 3. So we sort of did number 1 and number 2 were kind of the same, 3 and 4 were kind of the same. Example 5 is a little different. We're going to use the same setup just to be consistent, but I'm going to let you know now it's a little different. So don't fall asleep. It is different. I know. A solution of pure antifreeze is mixed with water to make a 65% antifreeze solution. How much of each should be used to make 70 liters? So I don't know if any of you guys have ever helped your parents put antifreeze into the car. You don't want to use straight antifreeze. I guess you could if it was really cold. But typically you buy a concentrate, you mix it with water, or sometimes you can buy it pre-mixed, but then you pay more. You end up paying for water, which is silly because you can get water pretty cheap. And a lot of them are just 50-50 the way that they're set up because that's easy. You can like put in 2 quarts of antifreeze and 2 quarts of water and just kind of mix it that way. But for some things, you have to do a different percentage. So this one, we want to make a 65% antifreeze solution, and we're looking for how much of each we need to make 70 liters. So they didn't give us a whole lot of information, but we're going to set up our table kind of the same. So we're going to do our 4 lines. And so we're mixing on the left-hand side. It's always what you're mixing together. These are all mixture problems. So we have antifreeze, we have water, and then we have the final product. You could kind of call that a total if you wanted to, but we're looking at it as the final product. And then across the top, it's always amount and part and final. Okay? So we're going back to percentages again. We used some percentages yesterday. So we don't know the amount of antifreeze. I guess we can just call that X. We don't know the amount of water, so we'll just call that Y. You could use A and W if you wanted to. Yeah. A and W, like this store. All right, but we do know how much total we're going to make. What goes right here? How much total? 70. We're going to make 70 liters. And so this is the amounts. And so this first column is where we're going to get our first equation. So this is where we're going to get the equation number 1. So if you wanted to go ahead and write x plus y equals 70 over here, basically it's just the antifreeze plus the water is going to add up to 70 liters. We don't know how much of each we're going to put in there, but it's going to add up to 70. Okay? Now the part column is where we either deal with prices or percents. It just depends on what the problem is. This one is percents. And so this is what's weird. We know that the final product is going to be 65%. So I'm going to change that to a decimal, 0.65. We're trying to figure out the parts. So antifreeze is 100% antifreeze. So we can just call that 1 because antifreeze is 100% antifreeze. And the water doesn't have any antifreeze in it. So we're going to call that 0. That's what makes this problem a little bit weirder because usually they'll be like, okay, we have a percentage here and a percentage here. We're going to mix them together, make another percentage. In this case, it's straight antifreeze and straight water. And so it's 100% and 0% in each piece, but we're going to mix them so that it's 65% antifreeze. Okay? So if we multiply each of these across, x times 1 is x, y times 0 is 0, and 70 times 0.65 is 45.5. And so we're going to use this column to do equation number 2. So basically I have x plus 0, so I can just write x equals 45.5. Do you see what's kind of cool that just happened there? We already know one of our answers. So x, if we go back, was the amount of antifreeze. If we look how we're measuring it, we're measuring that in liters. So that means we're going to use 45.5 liters of antifreeze. Okay, and then we can subtract that from the 70 because we know that 45.5 plus y equals 70. So you're just going to subtract this from the 70 that we're trying to make. 70 liters total. And we get y equals 24.5, which means we'd use 24.5 liters of water. So this one, the system of equations, really wasn't much of a system. It just kind of fell out because of the zeros. But you can solve it using the exact, so the reason I like to use the table is we can use the table for every single one of these problems. And then we don't have to think terribly hard about this problem being different than others. On some textbooks, they'll teach this differently than they do the other problems. I kind of like this method because on all of them, you make the table. Okay, so that is the end of part 2.